So we're just gonna be discussing this. Alright, so it shouldn't be too long. Within this entire thing, we're gonna have three sets of questions, right? That I want you guys to try out. Okay, so I would like you guys to just carry a pencil and a paper, right, and calculate as well, right? Just to have it with you when we reach those questions, right? Just to let you know. Now, for the principles of equilibrium, it's really a fundamental concept of chemistry that describes the state in which concentrations of reactants and products in a chemical system remain constant over time. Right? So we're generally looking at the point at which a forward and a reverse reaction, right, starts occurring at a similar rate. A lot of persons make the mistake saying that it has to be the same rate. It doesn't have to be, but usually similar rates, resulting in no net change in concentration of reactants or products. Right? So we're saying that we set a system in motion, the system starts moving in motion, right, from left to right, and left equals right. So it's basically something like that. In order to completely understand this concept, you have to really look at the concept of reversibility. Right? Now, in C-set chemistry, we made the huge mistake of looking at the fact that majority of our reactions are, just one pathway, right? One arrow, right? No, a good amount of the chemical reactions that we've looked at before are in fact reversible under different conditions, right? Some are reversible within their same conditions, right? So we tend to use those double arrows, right? So two half arrows to represent a chemical reaction in which the products and reactants can be reformed, right? Depending on what, it really doesn't depend. It really doesn't matter which way you look at it, right? Product formation, right, or reactant reformation, right, within the same conditions, right? So we're saying that if we have something like ammonia can decompose back to hydrogen and nitrogen, and the hydrogen and nitrogen can combine to form ammonia within the same situation, right? So the concept of reversibility is important for chemical equilibrium. So at equilibrium, the rate of the forward and reverse reactions are said to be equal, in which the concentrations of the reactants and products stabilize. So if you're gonna have a specific concentration of reactant, right? So let's say that the concentration of reactant was 2, specifically, right? At the beginning of the reaction, it would have been 2, right? For the product itself, it would have probably been, let me just have it over here, right? So this is the concentration of the product, of the reactant, right? The product would have been 0, right? So we're looking at the fact that in the beginning, we have full concentration of reactants, right? And because this is the beginning of the reaction, we would have no concentration of products, right? But the reaction itself would actually go on and on, right, pushing forward and backward until we have an equal number, right, between the two, roughly equal concentration between the two, and this is what we call equilibrium concentrations, right? So it's something similar to that, right? So let's have a look at this. So it doesn't generally mean that the reaction has stopped, right? Rather that the rate of the forward and reverse reactions are balanced, leading to a dynamic equilibrium, right? So it's balanced. I rather the word balanced over the word equal, but I put the word equal there because at the Cape level, a lot of persons tend to accept the word equal, but please remember, it does not have to be equal rates. It can just be balanced, right? So it's something like that. Any questions or concerns so far? Alright, so chemical equilibrium is governed by the principle of microscopic reversibility, which states that if a reaction can occur in one direction, it can also occur in the reverse direction. And this principle is encapsulated in the equilibrium constant K, right? The equilibrium constant K is actually expressed over around 5 different topics, right? But specifically here, we're going to be talking about Kc and Kp, right? So K in this on this slide, right? Which is the ratio of the concentrations of products to reactants, which which um which each specific concentration is raised to the power of the stoichiometric coefficients in the balanced chemical equation, right? So the last time we looked at this, the last time we met, we looked at the rates of reactions, right? We looked at constructing a rate law, we looked at constructing rate, the orders of reactions, looking at all those type of stuff, right? Now the rate law, you guys would remember that. So the rate is equal to K times the concentration of both of all the reactants, right? The products of the reactants brought to the power of their stoichiometric coefficient. So it's similar to that because rate constant K is still a constant K, right? And all these constant K's work in that specific way, right? It all has concentrations of specific compounds or specific substances brought to the power of their stoichiometric coefficient. Any issues so far?
No, sir.
All right. Okay. So that's basically it. All right. So just letting you guys know as well, I am completely sick. Right. So I am sick right now. So if I stop in the middle to just take a breath or to drink some water, then yeah, I'll let you know. All right. But I am going to push through because I made a commitment. All right. So let's have a look at this now. Chemical dynamics. Now, chemical dynamics is one of the things in the syllabus that you guys need to look at, right? So I have the syllabus right here, and it says to state the characteristics of the system of a system in dynamic equilibrium, right? And that's actually the second thing. So first we need to explain the concept of dynamic equilibrium, right? So a dynamic equilibrium itself, right, is a concept that applies to both chemical and physical processes, right? So you need to understand it chemically and physically. Right? I have two examples here, so it should be fine. So it describes a state in which opposing processes occur in equal rates, right? But I put in brackets here, rates don't have to be equal, but most times they're very close, right? Resulting in a balance where there is no net change in observable properties over time. So there's no net change. So what are these instances in when there are no net change, right? Or when there is no net change? Chemically, we can look at it in this way. In a chemical reaction, dynamic equilibrium occurs when the rates of the forward and the reverse reactions are roughly equal. Following? Everybody's following so far? Everybody's good?
Yes, sir.
Right? So the rate of the forward... Oh my. Not the pen, not... The pen is not penning. Alright. The rate of the forward and the reverse reactions are roughly equal. Alright, so this means that while the reactants continuously create products, the products continuously convert them back to reactants. Right? So you're not going to have an overwhelmingly larger concentration on one side. As a product is created, a good amount of that product will be decomposed, right, or put into the reformation of the reactants themselves, right? So as the forward reaction occurs, the reverse reactions occurs within a roughly the same rate, right? So at dynamic equilibrium, the concentrations of the reactants and products remain constant over time. So the concentrations must remain constant, right? So what we're talking about, is generally constant, right? Obviously, there are going to be fluctuations within concentration as products and reactants form or reform. Obviously, there are going to be minute changes, but when you look at it, the overall picture, the big picture, the concentrations, the change in concentrations would be so negligible, you can say that the concentrations themselves are equal on both sides, right? So we have to look at that. Also, the reactions have not ceased, they have not stopped. So it's a constant cycle of creation of products, right, and recreation of reactants. Okay? So instead, they continue to occur, albeit without any observable change in concentrations. Any observable change, right? So there are minute changes, there are microscopic changes, there will always be changes, but there are no observable changes, right? From if you look at it from a larger view, right? So we just say that the concentrations are equal. So, for example, in the Haber process, right? So this is the Haber process right here, the creation of ammonia, right? One of the most important reactions to ever grace Earth, right, or human history. So the Haber process itself actually led to the creation of a lot of types of ammonia, nitrogenous fertilizers and stuff like that, and ended hunger in some regions of the world as they were able to actually rapidly produce fertilizers to create much more food. Right? It can also be used to create explosives, right? But we're not going to really talk about that. But if we consider the Haber process, nitrogen plus hydrogen gives us ammonia in this case, right? And this is balanced. It is it's not giving balanced, right? But you have the Haber process there. At equilibrium, the rate of the forward, which is the formation of ammonia, would equal the rate of the reverse, which is the decomposition of ammonia, right? As a result, the concentrations of nitrogen, hydrogen, and ammonia remain constant, and the system is in dynamic equilibrium, right? So as long as the formation of ammonia and decomposition of ammonia remain fairly constant, right? The rate of that is fairly constant, right? What is the rate specifically? Can anybody remind me what the rate is? What is rate? Let me just get a reminder quickly. No brave individual knows what rate is? No, Sam, I did something wrong. Something terribly wrong.
The
Go ahead.
speed at which the chemical reaction occurs.
Repeat?
The speed at which the chemical reaction occurs.
Okay, that's lovely. But in relation to the rate, a rate equation, right? So rate itself, because when we're defining things now, we'd love to include equations. So rate is the formation, right? So rate itself is the formation of products. So let me just put F, right, of the products or reactants over unit time. Well, over unit time, right? So we tend to want to use that, right? Examiners or persons in STEM tend to want to use equations in assistance of, to assist our definitions, right? So it's the rate of formation of products or reactants over time, right? So that's what we're saying here. So if the rate of formation of ammonia and the rate of decomposition of ammonia are roughly equal, then the concentrations of nitrogen, hydrogen, and ammonia itself remains fairly constant, right? And this is what we call a system in dynamic equilibrium. Now, I haven't described all of the characteristics of dynamic equilibrium just yet, but we're going to get to that. All right, so we're going to get to that. So physically, right? So note that, dynamic equilibrium can be understood chemically and physically. Physically, this is going to be more useful to you when you talk about Raoult's law and all those different types of laws within Unit 2 chemistry. But dynamic equilibrium is also observed in physical processes, particularly in those involving phase changes, from such as melting, freezing, evaporation, condensation. All these different phase changes can occur within equilibrium, dynamic equilibrium as well. In these processes, molecules transition between different phases, solid, liquid, or gas, right, for the main ones. But at equilibrium, the rate of transition from one phase to another are equal. Now, I know that everybody here has seen a bottle of water before, right? Everybody here has seen a bottle of water. If you leave half of the bottle filled with water, right, and close the tap, you close the entire system, right? What would actually happen physically within the bottle itself is that water would be evaporating into water vapor, and water vapor would be condensing into the water, and that will happen at such fast rates, so let's say at such fast rates that it will form an equilibrium, right? So over time it will form an equilibrium. So in closed water bottles, you have an equilibrium forming, right? As liquid water becomes water vapor, and as water vapor becomes liquid water, right? So that exists all around us, right? So it exists within closed systems, and that's one of the characteristics of dynamic equilibrium, right? So this type of process here. So for instance, consider the process of water evaporating to form vapor and condensing back into the liquid. This happens within every single bottle of liquid that we have, right? There's always evaporation and condensation constantly occurring at the roughly the same rate in dynamic equilibrium. So dynamic equilibrium is mostly all around us. I'm receiving a call, but I will not take it. All right. So at dynamic equilibrium, the rate of evaporation equals the rate of condensation. So as a result, the amount of liquid water and water vapor remains constant over time, and the system is in dynamic equilibrium. Everybody fine so far? Go ahead.
Yes, sir. Sir, so it's a case where nothing is leaving the system, so it
Nothing.
means that equilibrium, right?
Mm-hmm.
Okay.
Nothing is leaving the system. That's what the close, because remember we have open system, we have closed system, we have adiabatic systems, we have multiple systems, right? But we're just looking at closed system, right? So let's look at this. What are the criteria for dynamic equilibrium? What are the criteria? So let's look at the first criterion. It must be reversible. If this reaction itself is not reversible, it cannot be in equilibrium. Why? Can anybody tell me why, if the reaction isn't reversible, it can't establish a dynamic equilibrium?
Sir, well, is it a case where if a reaction isn't reversible, we have more of one thing over the other? Like for example, more products than reactants. So we're
Well,
not having that balance.
well, true. Not only that, there's a little bit more to it. Think about the process of a one-way reaction. Because the reaction is only going one way. Go ahead. I think somebody unmuted.
It was me again. Sir, is
Yeah.
it that there isn't a constant like formation and replacing
Mm-hmm.
of reactants and products?
Lovely. So there's not a form. There's not. Well, let's look at this. If we have a one-way reaction, the reactants will create products until no reactants are left, and all we have is products. So if there is no reversible process, we do not have the decomposition of products to reform reactants, right? So once the reaction happens, it's just done, right? So reaction start, reaction stop. Within equilibrium, we must note that the forward and backward reaction or the forward and reverse reaction are constantly happening every single second, every single day. It doesn't stop, right? Unless you stop it, it doesn't stop. Right? So dynamic equilibrium occurs in reversible reactions where reactants can convert into products and products can convert back into the reactants. Both the forward and reverse reactions are simultaneously occurring at the same rate, roughly, at equilibrium, right? Constant concentrations. So at dynamic equilibrium, the concentrations of reactants and products remain constant over time. So this means that the rates of the forward and reverse reactions are roughly equal, resulting in no net change in the amount of substances involved in the reaction. Right? So, okay. So one thing that I kind of see a lot, right, from last year's group, is that some persons tend to look at reactions and say that, oh, the products and the reactants must have literally the same concentration. Not necessarily, right? They must have constant concentrations, right? If the concentrations happens to be equal, then that would be a very pretty question, right? But it doesn't have to be equal. It just has to be constant, right? So the concentration of the product could be 5 molarity, right? 5 moles per dm cube, right? And the concentration of the reactant could be 0.2 moles per dm cube. As long as it's constant in dynamic equilibrium, it's fine. Alright, so it doesn't have to be equal concentrations. It has to be constant though. Your concentration can't be doing all sort of stuff. Right? So it needs to be constant. That's one thing. The dynamic nature, despite the appearance of stability, a system in dynamic equilibrium, or a system in dynamic equilibrium is dynamic, right? By nature, dynamic means what? What does dynamic mean? You have dynamic versus static, right? You see, it's roughly the opposite of static. What does dynamic mean? I'm asking in your own words, guys, by the way.
So you're asking what dynamic means?
Mm-hmm.
Sir, the ability of something to like change or adapt over time.
Lovely, right? So the ability to change or adapt over time. Okay, or something that changes or adapts over time rather than being static, not changing. So constant change is important, right? So that's what dynamic speaks to. So the dynamic nature, right, of the equilibrium is important. Molecules are continuously interconverting between reactants and products, but there's no overall change in concentrations, right? So it's dynamic in the sense that you have continuous reactions happening, right? So it must be continuous, right? So it have continuous reactions happening, but everything remains constant overall, right? The concentration remains constant overall. Okay, so it's a little bit of, it's kind of supporting the previous slide, right? But in and of itself is speaking about continuity. Okay, so Shanique said flexible for dynamic. All right, so flexible not in this case specifically, but it is something that you could say for dynamic. It's all right. The macroscopic of observables, right? So what do I mean by macroscopic observables? While there is no net change in concentrations, other macroscopic observables may still change. Basically, the things that you can see can still change. For example, in a reversible chemical reaction, the color of the solution might remain constant, but other properties such as pressure, temperature, and density might still fluctuate. So not because the temperature is changing means it's not in dynamic equilibrium, and not because the pressure of the gases are going up and down means it's not dynamic, right? So it's something like that. So these things can still change overall, right? But these properties specifically, not talking about color, these other properties can change, right? But the system can be in equilibrium at the same time, right? Because when we're talking about endothermic and exothermic equilibria, right, then there will be temperature change. There has to be temperature change, right? So temperature can change, right, somewhat, right? I'm not talking about that, I'm not talking about a violent increase in temperature, but it can change, right, while remaining in dynamic equilibrium. And the last thing, the systems in dynamic equilibrium are typically closed systems, right? Typically, they're closed systems. So meaning that no substances are added or removed from the system during the process. If the system wasn't closed, why wouldn't dynamic equilibrium be established? That's a question. If the system wasn't closed, why wouldn't dynamic equilibrium be established?
Sir, because you're having a loss of something from this system, would it be energy or I don't know?
No. Energy can leave the system. Closed system speaks to the substances, the matter itself. Right? Energy can still do thing. But speaking about the substances themselves. Go ahead.
Sir, so it's like the loss of like a reactant or product from the system, so therefore there would be like no recycling.
Okay, it seems like we haven't developed. Alright, I understand what you're saying completely, by the way. but chemical vocabulary is important. Alright? You said recycling, interesting. But yeah. So we're saying that we wouldn't have a forward and reverse reaction as much because we're saying that as we form product, the product gone and some of the reactants would be gone as well. Right? So remember that the concentrations have to be constant. If we do have a closed system, how are the concentrations going to be constant? And remember that the product must turn back into the reactants, right? If the product is more volatile, it will just float away or will exit, right? And it will not be able to reform the reactants. If it's not a closed system, dynamic equilibrium cannot be established, right? Because everything must remain in the system, right? So once there's a decrease somewhere, right, then dynamic equilibrium will be broken, right? But not forever, because if you open a system and you close it back, then dynamic equilibrium will be re-established due to Le Chatelier's principle. I'm going to talk about Le Chatelier's principle. Okay? Are there any questions so far? Yes, no, maybe, kinda, probably.
No.
Alright, lovely. Just drop ones in the chat if we're ready to continue. And this is where your calculators and your pencils and your paper will be necessary. Because we're going to be working some questions, Alright? Okay, so let's have a look now. So the equilibrium constants Kc and Kp. I know that you guys would have probably seen this already, so the questions would be really, really easy for you. But let's have a go over of what their equilibrium constants are. So let's start with Kc. Kc is the equilibrium constant expressed in terms of concentration. Kc, concentration, right? Literally it's there, right? Usually in moles per liter or moles per dm cube. We tend to use dm cube, right? So of the species involved in the chemical reaction. So it is defined for the reactions, right, occurring in a homogeneous phase. What does this mean? Can anybody tell me what a homogeneous phase means?
Uniform.
LOL. Uniform. Yes. Uniform phase. Lovely. Right. So all of the phases for all different substances must be the same. So you can't have gaseous plus aqueous plus solid equals whatever. Alright? We must be able to find the Kc typically within aqueous solutions, right? Typically dissolved, right? So that's how we get our concentration, because concentration is how many moles exist within this volume, right? Therefore, it is aqueous solutions we tend to use Kc with, right? So the value of Kc remains constant at a given temperature for a particular reaction, regardless of the initial concentrations of reactants and products, right? So it remains constant at a given temperature. Alright, but we're going to talk about all those different things and what happened to Kc when temperature change, etc. Right? And it tends to be the same thing with Kp. So Kc is defined, right, as the product of the the product of the concentrations of the product actually divided by the product of the concentrations of the reactants, right? All brought to the power of their stoichiometric coefficients. Really, really simple. So in this case, where we have A amount of A and B moles of B gives us C moles of C and D moles of D, right? Kc is going to be equal to the concentration of our products. So let me erase that. Products first, right? The concentration of the products brought to the power of their stoichiometric coefficients, where you can see that they're the C there and the D there, right? And you can see the C here and the D there, divided by the concentration of the reactants over here, right, brought to the power of their stoichiometric coefficients. When you start to hear about a constant, K, products over reactants must come to mind. If it don't come to mind, pack up shop, alright, go home. Alright, so products over reactants. Everybody good?
Yes, sir.
Okay, lovely. Notice that the rate constant K, right, is similar to this, But the rate constant K is it with respect to reactants only. So that's why we did not bring it over the product of of the concentration of products, right? We did not do that with rate constant K because it only focuses on reactants, right? So the rate constant K is one of the only ones that, well, one of the only ones that do that. But Kc and Kp, products over reactants, right? So it's basically that. This has Kc prime, which is basically the same thing, which is 1 over Kc, right? Which is just the opposite. You just invert everything, right? But we're not going to be looking at Kc prime anyways, but it's really easy to see. But yeah, so that's what Kc is. So the equilibrium constant Kp now. Kp is the equilibrium constant expressed in terms of partial pressures using usually in atmospheres, right, of the gaseous species involved in a chemical reaction. So it is defined for the reactions occurring in a gaseous phase involving gases, right, or involving gases. Similar to Kc, the value of Kp remains constant at a given temperature for a particular reaction, regardless of the initial partial pressures of reactants or products. So Kp is generally the same thing. So the general equation for the homogeneous gaseous reaction at equilibrium would have this, right? I remember you can only calculate Kc and Kp at equilibrium. If your reaction is not at equilibrium, you cannot calculate it, right? So you need to get it at equilibrium first. You need to find out the equilibrium concentration or the equilibrium partial pressures before you do anything with Kc or Kp. And that is where your ice table will come in, and we'll discuss more about that. Alright, so it's generally the same thing, but we use P, right? We tend to use P to denote the partial pressure of the substances. Alright, so we're going to have to find the partial pressure of everything due to Dalton's law, and I know that you guys have gone through all of that already, so this is just mere revision. So if I'm moving too slow, just let me know. Am I moving too slow?
No, sir.
Right. So hopefully I'm not boring anybody to death. Alright, let's go. This is Kp. Really, really simple. Alright? So the pressures, the partial pressures of the products over the partial pressures of the reactants brought to the power of their stoichiometric coefficients. No issues. Alright? No issues at all. There should be none. Alright? We're going to talk about the values of K a little bit later. Right, so we're gonna talk about the values of K actually. I actually have a repeated slide in it about it. So when we finish going through everything, then we talk about what happens here, right? Especially when we completed these questions. So surprise, surprise, right? We have 4 beautiful questions here, ready and doable, right? The important fact is that these questions are doable, right? So let's have a go at the first one. Well, let me see if I wanted the first one. Sure. The first one is fine. All right, so let's just do the first one real quick.